Hello and welcome back. We now want to look at the code that we can use to solve the example of a continuous casting with a conic supply vessel. So remember, in this example we have a conic supply vessel shown here, which has an outlet here at the bottom, and it's filled with molten steel up to a height h0, and at the bottom the radius given by r1. Here at the top at filling height h0 the radius is r2. And our task essentially is to optimize the radius of the outlet R such that it fulfills our requirements. In particular, that it empties within a given time, and also we need to take into account a change over time between different of these two different conic vessels, so that the operation, the production line, operates continuously. So our first model is using Torricelli's law, assuming that we have laminar and continuous flow. We ignore all effects of viscosity. We have an incredible liquid with uniform density, and in particular our radius here is much smaller than the other two radii, and we don't take any specific aspects about the outlet shape and so into account. We'll just assume all of this is circular. We ignore any effect from this. So if we all do that, and Torricelli's law gives us the velocity as a function of the height given by this one. So g is the constant of gravity and h is the height of the liquid. And then we can say that the volumetric flow through the hole at the bottom is given by the area times the velocity. So the volume change is the negative of the volumetric flow. And then we put all of this together. And since we have a cone and not a cylinder, the height also then depends, of course, on the radius. So depending on where we are with this, we can build a differential equation for the height as a function of time. So this is then the full differential equation that we essentially need to solve. So we could do this, of course, analytically, but here we want to use different packages for that. And before you forget then, once we have solved this, and we want to optimize this radius here such that we fill empty the vessel within a given time frame. So let's keep this in mind as we go along. So first of all, we start with our boundary conditions. So the initial height is 2 meters and 0.9 meters for the radius at the bottom, 1.2 meters at the top. So this gives us our constant slope for the conic vessel. And here now we assume a fixed radius of the orifice. This is what enters in small a. Here we have our radius. So we'll just do this between 0 and 3000 seconds. So we define our lint space for that, and also convert everything to tensors, because we need to work with TensorFlow. And here we have our differential equation. This is essentially the set of equations that we had before, now encoded in PyTorch tensors. And here we add one line to make sure that h is never becoming negative, because that would be an unphysical solution. So here we use the package ODA-int to solve the differential equation, right? And then we can look at the h values, and with this starting values, we get the curve that you're familiar with from the lecture slides. Now what we want to do, as we said before, is to optimize the outlet radius. We do this with a differential equation that we had before, but now we don't have a fixed radius. So our target empty in time is, from the discussion in the lecture slides, 428 seconds. That encompasses the time that we have for our continuous operation plus the change over time between conic vessels. So what we really need is a function that gives us the height inside that conic steel vessel at the end of the time, so at the end of 428 seconds, and that depends, of course, on the radius of the outlet. Now, obviously, we want to optimize such that the height is 0. Right? So we can then use later on, we'll come to that in a little bit, Newton's method for root finding to find the spot where this becomes 0. Now we have this function here, and everything needs to be torch tensors, so we want to work with all of the advanced capabilities of the torch library, so that only works if we have tensors. So if we don't have this, we also need to make sure that we have everything as a tensor and require gradients. Otherwise, we cannot track this for Newton's method later. Now you can see here we have this function and we have this function inside the function. So we have a function inside the function. This is perfectly fine Python code. Why do we do this? Well, inside here, remember from our differential equation, that depends on the area of the outlet small a here. We could make this a parameter, but unfortunately, the ODA method doesn't take any additional parameters. So each time we want to call it, this has to be defined. But now this is a variable. So the solution we take here is to define a outside the scope of the HDT. So inside here, this a is a constant. And then we can solve this. But for each call, a is now a variable because it depends on the radius of the outlet. Here we can now solve this now. So we can plot this first. We create our lint space for 50 steps and then call the function, and this is what it looks like. So we can add the known solution. This is what we will find out later, and you can see that depending on the outlet orifice, the height approaches 0. Now this is what we want to find out, so just that you know what should come out later. And how do we optimize this? Here we use Newton's method for this. So we can find the root of the function. So the root means where the function crosses 0 or becomes 0 with Newton's method. And so we can define this here, and the key part is that everything is in tensors. We have a conversions requirement, and if this is smaller than a tolerance, so if we approach 0, and then we take the gradient, right? And Newton's method is then we take the next iteration, this is the current one minus the value of the function divided by its derivative. And so we iterate all of that until we reach conversion. And here in the end is the code magic to prepare for the next iteration. So the next iteration means that the old value is now taken from the new one, and here we need to make sure that we detach it from the computational graph that we had before, and we make sure that we have the gradient so we can start again. We define a small convenience function that is essentially a wrapper around compute the height at the end at 428 seconds, depending on the radius. So we need, for Newton's method, some sort of initial guess. We'll take 25 millimeters. We need to guess to be reasonable, but of course not exact. Otherwise, there would be no point in this. And then we let it run. You can see that after only 8 iterations, we find the correct solution. Now we can plot this again. Remember, with the small a, that we need to calculate this, and then this is why we need to define the differential equation again. Call ODA, and then we can see that for this time at 428 seconds we reach 0. You can also take an iterative approach, and it's essentially taking the same differential equation, but you can say here, instead of solving the differential equation with ODE, and we can sort of discretize it, as you can see here, and then walk through this. It's the same differential equation that you can see here. Walk through this in discrete time steps, right? And then you can do the same Newton's method with this and find the same solution.